first of all, welcome to the today's sharing session. So I will share with you my slide first. Okay. Okay, right. My name is Muhammad Najib. As explained by my friend, Dr. Nizamuddin is still my friend from my old school. We are studied at the same school last time. So I write it down this diploma in here because not many of you know about these terms. I have completed my degree in Germany. So after completed that degree, they call it as diploma. So I got at the diploma in lah. In is for the engineer, and I also further my master in Germany, and then uh, I continue my PhD in USM. Okay, currently I'm at the penyelaras pendidikan, and for the today's topic, it's a very long topic. Actually, I will concentrate on the optimization of a structure design before you manufacture it. Okay. Why is 3D printing? Because 3D printing is a trend. It's a trend for the future, and it's trend right now. Okay. It's predicted maybe in the future the 3D printing will use. Okay, it will be commonly used. It's just like a common printing, common printer, and the metal printer will be very common in the future, and it is very interesting. But for to do the metal printing, the cost for the powder and for so on, it could be quite expensive. So even now, okay. So if you want to do the printing, so it's better for us to optimize the structure. So what I'm going to share with you today is how to optimize it. And the best thing is what I want to share to you today is I will share to you using a free software that available online. So what type of software that I will use, okay? And also I will share with you the case study, okay? Case study 1, case study 2, case study 3, and so on. And then there will be a Q&A session. Even during the sharing, if you want to ask anything, so you can ask, okay, interview, because otherwise actually I don't know, because I feel like I'm talking with a screen, but lucky I see some face, okay, here, okay. And so when I present, so if you have any questions, then you can ask, okay. I am not going to pretend that I'm expert in all field and this, but what I'm going to share with you is what I know, okay. So we share, we are sharing knowledge with what we know, okay. In what I know, right? Uh, I prefer to share by sharing like a simple case study like this one. Okay. As I said earlier, I want to. Okay, the goal of the today's session. Okay, there are two goals, right? First one is I want to demonstrate to you demonstrate to the audience today to demonstrate how to save cost, okay, by using the simulation optimization. Okay, why you are using the simulation optimization? Because everyone and every researcher, okay, have a computer, right? So we all have the computer, okay. To complete this kind of simulation, if you have, for example, Intel i5 or compatible, this is good enough. Of course, if your processor is better, then the difference will be the solution will be solved faster. Okay. Why you want to do the optimization? Because you want to avoid the try and error fabrication, which is most of the time is being done by many students, many even by researchers, or even by myself before I know how to know how to do the optimization and so to use this software. So we normally use try and error and so on. Okay, and actually, by doing the simulation, it's not we have many options. Okay, to test our structure virtually and to do optimization and have the insight, right? How we are going to save cost by reduce the uh, mess of our design, right? Okay, the secondly is to solve the simulation optimization by reducing on average 50%. Okay, so be given given the structure that we have, so we want to reduce 50% reduction, so that 50% mass reduction will be our constraint. Okay? Constraint of the model during the simulation. Okay, so uh, and then by doing so, we also know have a better insight. Okay, we know we have a better insight how to optimize it. Okay, how it's going to look like, in which mesh is in at which part is important, and which mesh at which part another part that we know. Okay, this is important or this is not. Okay, it is being calculated by the the computer, right? It is being calculated by the computer. So what I'm going to use, okay, what I'm using now in my laptop, okay, I'm installing the software ANSYS 2021 R1 version. Okay, that you can also use the R2 version, academic version. Okay, once you install it, right, it's valid for 1 year. Okay, it's valid for the 1 year. Say, and the examples that I'm going to show to you, okay, they are about 3 to 5 examples. Okay, it depends how many examples can I share with you. So try the maximum I have. If I'm going to show to you is 5 examples. Okay, the minimum I tried to share with you the 3 examples. Okay, all these examples I solve it. I used the topology optimization using this ANSYS 2021 R1 academic version. Once you install this one, right, it is valid for 1 year. Right, it's valid for the 1 year, and you can solve this structural problems up to 125,000 elements, right? Actually, you also can solve the CFD problem, fluid problem. But for the today's sharing, I only share with you the structural optimization problems. Okay, for the CFD problems, CFD's software, if you install it, you can use specifically. I'm referring to the Fluent software, right? You can use up to 512,000 notes. This is the free version, right? The free software. This is free for students. Okay. And now, where you can find this software? So you just go to the Google, okay, and then you type ansys.com. Okay. Once you type ansys.com, then this page will appear. Okay. So this page will appear. So you see up here, there's a student and academics, right? There are students and academics. So just click this one, right? So you just click the students and academics here. So this answers academic. So if you are use this, if you are now at the stage of learning, so you can consider yourself as student, right? So when you are a student, you are free to use this one, this version. Okay, there are a free student software, right? Uh, okay, free student software. Try click. Start here, right? So you find free student software downloads, right? So you go to here, all right, and see student, right? So you can click download now, right? Once you click download, you see there are ANSYS Student 2021 R2. Okay, they are also a prior release. Prior release, it means For examples, your friend use ANSYS Student 2021 R1. Okay, for example, I'm currently use this version. Right? Uh, Once you use this version, when you install it and you see, okay, this is the built-in license, so you can use it, okay, until 31, okay, 31st of March, okay, March 2022. Okay, actually it's extendable. You can extend it, right? So it's extended. After this date, you can extend it and use it. But they will recommend you to use another version. So if you design using the prior version, you can always open it, right? So you can always open it. So it's stated here the license duration is renewable. So it is renewable for 12 months. So it's free of charge. Okay, when you are at the stage of learning, right? Either you are from company, okay, either you are students, you are freelance, but when you are studying, okay, this software, then you can consider yourself as a student, right? So you can install it and do it, okay. All right, so right, so this is the software that normally I use during my class with my students, okay, and also when doing the trainings and so on. Okay, this is the software that we use. Okay, I back to my slide, right? Okay. Any questions on the software installation and so on? Then,
everything's okay.
It's okay, right? You can also spare your question at the end of the session, or you can ask directly if there are any questions, right? Boleh ni lah, you can type in the chat box and we'll go to it later, right? Or you can unmute and ask directly. Okay, the next is the step for the topology optimization. Okay, why I explained before, I already tell why we do the optimization, because we want to save the cost, right? And to avoid the try and error. So we start at the initial design. The initial design can be any shape. It can be the existing design. Okay, existing design that we have or you have. Okay, they already serve the certain function, right? Already serve certain functions, but now you want to optimize it. Why? Because you want to do the 3D printing. Okay, for example, you want to do a 3D printing, okay, or laser. If you have metal 3D printing, then you can do the metal 3D printing. But when you want to do metal 3D printing, it's very important to optimize it first. Why? Because the powder is more expensive. The price, okay, is not the same like a normal material of the 3D printing. Even you want to use a normal 3D printing, also you can do optimization and so on. This kind of optimization is also valid if you want to do the fabrication process of others. I mean, for example, laser cut, for example, right? You want to do a laser cut and so on. Okay, uh, it, uh, you can also, it depends on your structure. Okay, certain shape, yeah, you can do the laser cut. Certain you have to do CNC machining and so on. All right, but what we are going to focus about the topology optimization. This is topology optimization is the method to optimize the structure. Start from the initial design, then you do the CAE analysis. This CAE analysis can be the finite element analysis, okay, because we want to look at the nature of our structure. For example, we know it has to withstand a certain load, right? So, or it fixed at a certain point. Or our structure, for example, we know that it will be used at a certain frequency. I mean, for the dynamic loadings, right? When you attach to the motor, okay, when you attach to the motor, and then when you attach to the certain structure, the moving parts, there are a natural frequency. Okay, so you want to design your structure to avoid that kind of frequency and so on. So you test it first, okay? And then after you test it, you see, okay, this is the shape that we have, and this is the load, and you can also say, okay, this is kind of deformation, this is the kind of stress that you have, stress of the structure, and also you can also see they call it the safety factor, okay, of the structure, okay. Of course, the safety factor depends on type of the strength of the material that you use and so on. And then you do the topology optimization. The topology optimization here, okay, in the there are also other software. Okay, there are also other software that can do the topology optimization. Okay, but this one is free. This one is free. Of course, if you use the full version, that is different. This is the version that I will show to you the example that I use. Okay, the example. Then you can use quite many many problems that you can solve using this free version. And good one is it's valid 1 year, right? Okay. Sometimes okay, the topology optimization software is very expensive, and normally it costs something. And normally it is not given that long duration. Okay, and now there's give the user 1 year, and even better, you can renew this software. I mean, it means it's not 1 year because you can renew it. Okay, so it's very good, right? So so you know how to do it. For if you want to decide to go to the full version, then it's up to your institution. But this one is the free version. You do the topology optimization. Normally at topology optimization, there are certain constraints. For example, constraint will be optimized based on natural frequency. And then another constraint is based on the energy and strain energy of your structure. I mean, based on your deformation, you want to optimize it. For example, at the same deformation, okay, you want to optimize the structure, or based on the stress of your structure, you want to optimize the topology that optimization. Okay, and then the next step is the smooth results. And smooth results, I mean, once you do, there are certain mesh that has been taken out, right? There are certain mesh that have been taken out, and you smooth the results. I mean, there are certain operation, okay, in that software, or you need to redraw that shape, okay, or you can redraw that shape, and then based on the shape of the recommended by the topology optimization results. Okay, after that after you redraw or you smooth the results, smooth result, I mean you change the STL file, you change the file, the facet geometry to a solid geometry. It means the smooth result, right? The smooth result of the geometry, and then you do the validation. This validation, then you do the validation after you change. You do the validation one more time in the software, right? In the software. The good thing is after you optimize it, to test it, even need to test it, you do it again in software. All right, this is how marvelous it is. So after you test it, you see, oh yes, that's right. This structure has been optimized based on these results, right? Okay, then it is completed. If you have the budget, for example, so you say, oh, I have the budget, so you want to, or you have the metal 3D printed, so you want to do it, and you want to fabricate it for a certain purpose. You can proceed it by doing the fabrication or validation using the real structure and so on. Right? Okay, this is the 5 step of the topology optimization using ANSYS. Okay, now we go to the test case study 1. So I like to share the test case study 1. Okay, actually I have opened this software, right? So you can see this is the overview of the software, right? Actually there are many possibilities, but we are focusing on the topology optimization. Okay, but let me explain first about this problem. What we want to optimize, right? This is we have a simple plate of length of around 305 actually, but when you draw it, it's become 304.8. It's okay lah, right? This is just an example. Okay, this is an example, but this is the the dimension that I've drawn, the 304.8. Okay, this is square shape, and then there are a center hole, where the center of the hole is fixed to a certain point. Okay, now this example is you want to maximize the fundamental solid structure, 50% of this material of this original structure. We want to optimize 50%, all right? 50% of this, 50% of mass, okay, of this structure. For example, we want to optimize based on the natural frequency. Okay, we want to optimize based on the natural frequency. As I told just now, so optimization can be of many reasons, all right? It can be based on the strain, deformation, and so on. But this is, for example, we want to attach, okay? We want to attach this shape on the moving parts, all right? Let's say we want to attach, okay, this at the moving parts, all right? It can be a motor vehicle and so on. So, but you want to optimize it, right? So so the problem I solved the problem. This is the approach that I used a 2D plane stress for node control elements, and then I solved use the modal analysis. For those who have familiar with the dynamic analysis, okay, maybe are familiar with the modal analysis. So at the modal analysis, we solve for the 6 modes, and then the topology optimization is solved with objective to maximize the selected fundamental frequency. The question is why? Okay, why you want to do this? What is this natural frequency, and why you want to avoid this natural frequency? Okay, as you know, when you we want to avoid the natural frequency. Okay, we want to avoid a certain natural frequency when we design some things. Okay, we want to avoid, okay, any moving parts, okay, cause vibrations. When it cause vibration, then it will be there are natural frequency of that particular structure. Okay, and this in this example of structure, of course, I take a very simple one. Okay, we can do a many almost complex one, but better we will start a simple shape and see how it works, and then we can go on with the complex structure. Okay, but first you need to understand why you want to avoid it, because you want to avoid that vibration. As you know, when the structure of your shape is equal to the natural frequency, the operating frequency of your motor, right? For example, your fan rotated at certain rotation, like RPM, right? So at that certain rotation, there's a frequency exerted because there are vibration, okay, vibration at your structure. Due to that vibration, if the frequency of that vibration is equal to the frequency of your shape just now, so it will be the vibration will be very high. Okay, vibration will be very high. I will show to you how to modify the design. Okay, and now how to modify the design? Yes, you can modify by 2 ways, right? By either you change its mass or you change its stiffness, right? Okay, the natural frequency is actually proportional to the stiffness, and if you reduce the mass, then the frequency of your structure will also become high. So now the way is to reduce some mass. Okay, you want to avoid that frequency. Okay, first I'll share to you how is the natural frequency looks like. Right? For example, we have a simple this is our simple structure just now, right? This is I solved it using this ANSYS 2021 R1 academic version, okay? The one that I've shown you before, okay? The one that I shown to you that I installed it, right? Okay. Of course, you want to install it. It's just like a SolidWorks software, right? It takes some time, right? But the space you require is also around almost similar with the SolidWorks. If you are familiar with SolidWorks, I think you'll be also familiar with uh, this software, right? So this is the I solve this problem using they call it modal analysis, right? In the modal analysis, all right. In the modal analysis, we want to find the shape, right? The shape of the mode shape, they call it. They call it as a mode shape. All right. So before, okay, when you define and then you go to you can define the material, right? After you define the materials, and then you do the meshing, right? It is a straightforward step, okay? Right? And then this is the modal analysis where you do the setting. Okay, for example, we want to determine the first 6 mode. What is the first 6 mode? First 6 mode, it means this structure at what frequency it occurs, the natural frequency occurs, and at what shape it takes place. At what shape it takes place, right? Yeah, we were going to do optimization, right? But before this, before that, I explained about the this problem first, right? Right. For example, this is the first mode shape that occurred at what is the frequency at 140 hertz, right? At 140 hertz, right? Okay, at 140 hertz. Let's say your structure, you attach this one at your motor, right? So, and when it's rotated at 140 hertz, you see the deformation is quite, okay, large. Okay, this is how it's vibrate. Okay, this is how it's vibrate. You see, it can goes up to 47 millimeter. The deformation goes up to 47 millimeter. In other words, right, the vibration is large, right? The vibration is large, right? So you want to avoid that one. Okay, how you want to avoid that one? We are doing the optimization, right? I will show you. Okay, and okay. Right? Okay. For example, when is this one, you don't know. Okay, macam tak nampak macam mana? Okay, you can click to this vector. You click this vector, then you can see how it's vibrated. Okay. Yeah. The direction lah, direction vector. Right? Okay. And then can go to the second, third, and so on. Right? Okay. Third and so on. Right? So, but in our case, okay, right? So up to now, you understand what is the mode shapes, right? And what is the natural frequency. This natural frequency is automatically occurs based on the stiffness of structure, based on the mass of your structure and how you clamp your structure, right? So we want to optimize. Okay. Now, what what are the thing that we want to optimize, right? So in this case, this is the setting for the topology optimization. This is the setting for the topology optimization, right? Okay, right. So in this case, I want to optimize, right? I want to optimize. I show you the modal analysis, the analysis type. Here, I want to optimize. I know that this structure, I want to attach it to the frequency of 150 to 180 hertz and so on, right? We want to minimize this structure. Okay, we want to minimize this natural frequency. Okay, minimize, it means the frequency will be at around at 150 hertz. So we do the definition. All right, yeah, this is the definition, and the objective is frequency to to maximize the uh, based on the model analysis and the mode that we selected. All right. And then there are response constraint. What are our response constraint? We want to reduce 50% of our mass. You see, this is 50% of our mass. This is, like I said, we want to optimize 50%, right? So when we run it, okay, so it will suggest to you how it looks like, right? Okay, this is how it looks like, right? So this is, it suggests to you that this, if you use this mesh, you maximize the natural frequency that you selected, right? You maximize the natural frequency that you selected, and then you go up here. You can test again what is your natural frequency after optimization, right? And then you can run it again. Okay, run it again and see. Okay, you optimize the structure or uh, or not. Okay, okay. This is okay. For example, right at this stage. Okay, I'll try to open this one. Fresh. Okay. This is what it means here. You export the results, right? The result that you optimize, and then you go to the geometry. This is what you do. Okay. At this stage, you want to do the validation, but before that, you want to redraw, or you want to take that structure that you have optimized uh, and proceed to the test or not. Okay, so this is at that stage, right? So you're going to do uh, the based on the shape that you optimize, so you have the better insight that how it looks like, how your optimized structure will look like. Okay, so if you want to do the laser printing, you want to do the 3D printing of that structure, then you can do it, you can proceed. Okay. Oh, slow skip. All right, so as you see here, right, when you introduce the mesh, okay, the natural frequency will be different, right? So this is the punya final test lah, right? The final test. Okay, the shape here you can redraw it, because there are also you can redraw, because in ANSYS there are the geometry here using SpaceClaim or using design modeler. You can redraw it in this software, right? It's not just the analysis, you can redraw it, okay, using this software. So I think that's for the test case 1. So we'll go for the test. Ya, saya try buka ya. Okay, this one they are using a space clip, right? Because in ANSYS there are two design software. The design software, it means you can design in this software, or you can import from the SolidWorks, you can import from the CATIA, you can import from other 3D models. Okay, you can import from other 3D model, and you can modify it in this software. This software called Space Claim or design modular. There are two software in ANSYS. So when you install the ANSYS, there's not only one software, it's actually multiples. Yeah, at left side here, you see there are analysis system where you can do the analysis. All this is free. This one you can do it, right? Okay, this is the design. You see, you can draw line, circle, rectangle, and so on, right? Right? Okay, this is the shape that has been recommended that you want to proceed, right? So Yeah, back here is the original shape. Okay, this is the original shape, and this is the shape that been optimized. Okay, the shape that been optimized, as you see, there are facet. Okay, there are facet geometry. Okay, facet format. Right. So you need to change it to solid if you want to do directly. If you want to take this structure directly and 3D print it, for example. Huh? But normally what people do, they will redraw. Okay, they will redraw the shape, right? You can redraw the shape here. Okay, you can redraw the shape, and then you do, when you redraw, then you have a, a better and smooth shape. But this software, they give you recommendation how, of course, the recommendation based on certain equation. There are certain theory back. Okay, but I want to show the hands-on approach only. There's, of course, there are mathematical models behind this software to solve this solution. Okay, if you see, there are sharp edges here, right? So it's better to redraw it. So you can redraw it, and then you based on this this original shape, right? You can redraw it and then do the analysis again. But if you want to take it directly, okay, just if you want to test it, so first you need to convert this one, okay, convert to solid, and then merge faces, okay. So once you do it, it's become solid. Then after it's become solid, then you can test it, right? You can do test it and so on, all right? And you can export it, or you can do the you test it first. Is it optimized or 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 or, or right? So this is for the first case, right? So I will close the first. Okay, any questions for the first one?
So far is quite clear. There is no question from the floor.
Ada. Okay, so I will proceed to the second example. Okay, this is the second test case, okay, where you can see in these examples, okay, there are a bracket, okay, there's a bracket, we hold this bracket, okay, we hold this bracket, at this there are two holes, right, cylindrical supports, okay, there are cylindrical support, okay, maybe with shaft, and then you apply the bearing load 1000 newtons and so on, right? So when you apply 1000 newton, and we have the stress of our structure. So now you want to optimize, we want to optimize 50%, right? We want to optimize 50% of our structure. Okay, we want to optimize 50%. What you see here, this is after the optimization. Okay, after the optimization, where the percent of mass of the original is stated here is 46%. Okay, if you see, the shape here is not very smooth at all, because I haven't complete the smooth operation yet. So either you do the smooth operation, or you can redraw your shape, okay, based on this one, you can redraw this shape, and then you can do the 3D metal printing, or even a normal, if you use a normal material, so make sure you input the 3D materials, 3D printing material during the simulation. So if you use the 3D printing, so you can input the material. The input of the materials can also be done, right? Can be done, can be customized, right? Can be customized, depends on your structure. Okay, so you can redraw it. Okay, you can redraw it, and then you can get this shape. Okay, example. This is another itulah. Alright, the second example. Okay, this is the second example. And then the nak buka ke second example ni? Nak tengok tak? Or proceed to the third one. Okay, kita proceed yang third one lah
Boleh je.
Okay, I proceed to the third case study. Boleh je. Saya tutup dulu.
Okay. It's okay
Sekejap
because we have another 20 minutes
Boleh. Okay.
for the webinar. Yep.
Sempat Okay. So I explain the third case study is the same. Actually, it depends on your model, okay, your actual structure. Then you draw it in your models, and then you do apply the load and so on, right? For example, in this third case study that I want, we normally what we start with our structure is just a simple square shape. So we know that we want to attach, right? We know that, for example, we want to attach the shaft at this point and then the load, okay, shaft at this point. We know, okay, this we know, but for example, we want to optimize this one. This is just a simple example of one illustration that we, all right? But let's say we start with a square shape, this square shape. Yeah, so you want to optimize based on this one, but we don't know which parts is important, which part is not. So that's what we do. Okay, what we know that okay, we fix at this point, we apply the load at that another point. That's what we know. Okay. So after we know that one, first we do the static structural. If you see here, okay, why we do the static structural? Because we want to see how the structure behave after we apply that load, right? Okay, behave after we apply that load. After we know that one, so we can export our solutions to the topology optimization. Okay, we export our solution to the topology optimization. Okay, in this case, we apply the force 1000 Newton at both sides. Okay, at both sides. We apply 1000 Newton at both sides. So this is our topology optimization constraint. Okay, first when you do the topology optimization constraint, you need to set okay, you need to set your objective. It means, for example, here minimize compliance. It means you want to minimize the strain energy. I mean, it based on the deformation. Okay, based on deformation of structure, you want to minimize your structure based on the response constraint 50% mass reduction. This is what I call to save at least 50% cost reduction by you stating your response constraint, okay, during your topology optimization. The response constraint here, you can also change, for example, you want based on volume, based on other cases, okay. But this one we specifically focus on the mass because we want to save the cost at least 50%, right? So that's why we stated the response constraint here 50%. All right. Where you put the response constraint here. You see the response constraint, mass, all right, and then defined by the constant percent to return 50%. This is the response constraint. You can change your response constraint to other value, right? They are also based on volume and other parameters. Okay, but here we specifically choose, okay, to optimize the mass, right? So that's our focus. We want to save money, right? And to save 50%. When you reduce, not only it become lighter, use not only the performance of your structure is better because it become lighter, is the cost of your manufacturing is also reduced because you use less material. Okay, so okay, those you for example now this the for the metal printings is the powder can be expensive, so you need to use wisely. Okay, you use wisely. Unless you are expert in the powder metallurgical, you are producing your own powder. But even you are producing your own powder, if the raw material, I think is also expensive, right? Now, so you need to use wisely. So how to do it wisely? You need to know. You need to know how to do the optimization, right? And then after you know how to know this optimization, only then you manufacture it. Okay, let's say you don't have this metal 3D printing. Maybe there are certain university providing service and so on, but for this particular shape, you can do you uh, apa dia panggil laser cut also, right? Because this shape, right? Okay, and this shape you can also produce by the laser cut. Even the title I put it a 3D printing, using the knowledge you have here, you can produce it using a laser cut. Most of the university and most of the company they have access or they have their vendor have the laser cut punya ni lah, right? Okay, this step can be right. So after you set the objective, okay, and then you set the optimization region. Okay, in the optimization region there are certain, for example, yeah, you exclude certain region, and then this is the what are the design that you want to choose and so on. So after it's calculated, okay, so this is the shape that has been suggested, right? Okay, this is the shape that has been suggested. Yes, you can export this shape and do the run again, do the validation, and then you confirm, right, yes, this is shape is good, right? So you can proceed to the manufacturing section. Okay, you can proceed to the manufacturing section. So you can put in your you want to design your AGV, or you want to design whatever you want to design. Okay, even you have the existing design, you want to improve it. All right. For example, you have the existing design. We have existing design, so you say, oh, how do I improve it? I don't have the drawing. So even in here in the university, they have a 3D scanner. Okay, they can 3D scan, but it's quiet time, of course, because when you do the 3D scan, it's not a solid geometry, right? Sometimes some shape you need to improve. You need to do the redraw and improve that shape, become solid, and then after that you can do the optimization, right? So in the university, in here we also have the 3D scanner. So if that's an existing design, so you can do a 3D scan. If a simple shape, of course, you can draw it directly. If it is a complex shape, we have also a 3D scan, and then do the optimization. And then from there, you can reduce the mess. Maybe if it is existing design, maybe optimization did not reach 50%, right? Maybe it did not reach 50%, but even so, 10% can be very, very valuable. Okay, if you are improve 10% of your structure and you are producing 1,000 parts, right, per day or even per month, okay, you are saving a lot of money. All right, you are saving a lot of money. All right, if the structure is very simple and you do here you can do you have the idea. All right, if it is already existing, if you improve, so maybe the target could be 5 to 10%. It's even 5 to 10% is good enough. It can be more, it depends, because we have to test it again in the simulation, right? You need to test it again based on the load of your structure and so on, based on the load of structure and so on, and then you test it again. Yes, you say, okay, this is good. Okay, this is good, and proceed, right?
Alright, Dr.
Nampak?
Najib,
Okay.
there is one
Otherwise, you
question
don't know,
from,
right? You don't know.
can you hear me, Dr. Najib?
Terputus lah, tak dengar.
Oh, tak betul. Okay. There is one question from the floor.
Oh, okay. Does it mean if the shape is efficient, the lower the cost of the 3D printing? Okay, the cost of the 3D printing, because here we are focusing on, we assume that when you do in this step, we assume that when you use less material, then the cost will be less. Okay, this is what I assume, because when you do the laser selective manufacturing, for example, the metal you melted, okay, you melted that, okay, you are it depends also how you arrange, right? It depends also how you arrange, if you arrange your parts in your during the process. Okay, that one I will not focusing on. Saya tak fokus lah. That one I will not focusing on this lesson right now, because it also depends on many other parameter when you are talking about cost. But now we are focusing when we do the assumption, when you reduce the mass, because when you reduce the mass, the cost will be lower. Maybe it's not directly 50%, 50%, right? Because there's another cost, right, involved. This must be there's another cost. When you do the parts, maybe you need a support structure. Okay, you need the support structure using the 3D printing. The support structure also costs something. You also need to know how you are going to place it, right? You are going to place it. If you arrange it, okay, like this, maybe it's different. Okay, you arrange it to vertical. Maybe you can put many more. Actually, in this ANSYS, there's also the additive manufacturing simulation, but that one is not free. That one is not free. That additive manufacturing modeling, it means you can model your 3D, how you are going to do the 3D printing, including the structure. You do it in the ANSYS, but that one is not free. So that's why I'm focusing on how you optimize the structure by doing assumption. When you use lesser material, then the lesser the cost. The cost, of course, not 50% material means 50% apa duit itulah, betul tak? Sebab dia ada parameter. It can be, but of course you use the lesser material, then you have a less punya ni lah, right? Specifically for 3D painting lah, you use the less powder, so maybe that powder you can use for another purpose, betul tak? Kamu boleh buat dia punya simulation time lagi lah, during the printing, how long will it takes, right? And then what is the support? Do you need the support structure? If you can optimize that support structure itself, then you can also save money, right? Maybe you optimize it, but after you optimize it, you say, oh, this shape, if you want to use this shape, you need support structure. Then maybe it costs more, because it depends on how you arrange it, right? But my focus here is to do the optimization of this structure, and then save cost. Itulah. detail lagi sangat. Mungkin ada yang di sini is very expert on 3D printing, they'll know more than me. Okay, but my specialties is do the optimization of the structure using this ANSYS lah. But I use this one, and then we export it, we do the 3D printing. Okay, this is my interest and my specialties lah. Directly on 3D printing, bukan saya lah, memang saya tahu tak banyak lah. But I know the cost is not directly proportional. Tak boleh kira proportional gitulah kan. Mestilah banyak cost lagi. Ada, okay? Boleh Khairul Nisa. Okay, terima kasih tanya. Kat mana lah? Okay, so we proceed, right? So from here we know that this shape, okay, most important, if you want to first is the save cost tadi lah. Do the assumption that when we optimize the structure, we save the cost. Kita kata gitulah. Because last time we have invited one speaker from BMW lah. They do one optimization of that structure that they use for the racing, Formula car racing. Satu parts. Okay, even that parts they said, oh, that particular parts they need 1 year. Why 1 year? Because there are a lot of other parameters lah. Okay, a lot of the other parameters that you need to consider. For example, during the support structure, and then 1 year means there are multiple punya optimization lah. Dia buat banyak kali, bukan sekali lah dia ada. Dia dah improve support structure ni and dia improve lagi lah. The cycle takes time for 1 year. Okay, takes time for 1 year. But this one, if you're, for example, you're expert in the manufacturing punya ni lah, yang katakan ada 3D metal printing, dia cakap, okay, you need to optimize it because you want to use less material. If you say like so, okay, you want to use less material because when you melted this line, okay, you only use this material. This is you are not melted kan. So maksudnya guna save cost lah tu maksud saya. Kecuali tiba-tiba kamu akan guna support structure yang tu lah. Tapi yang nak including the support structure modeling, kena buat modeling with support structure. Modeling with support structure and modeling additive manufacturing, maksudnya dia boleh buat additive manufacturing, tapi yang itu tak free. Okay, itu kena bayar. Bukan kena bayar lah, maksudnya there's another version, software version, ANSYS version, but that one is not free. Okay, mana ya? Okay, then
Dr.
there's
Najib.
another example.
Hello, Dr. Najib. We almost at 11 a.m. right now. Maybe you can point out a little bit 1 or 2 points, and then we need to wrap up our webinar today.
All right. Okay. This is so I'll just show to you that this another example. This is not constraint. 50% mass reduction. So we have this shape, right? Okay, this shape and so on. Okay, at least you know how you want to optimize your shape and then use the structure. It can be for the purpose of for the reduction of the cost, or it can be to optimize, for example, the performance by using a lighter material of your overall design. Okay, this is another test case study. Okay, it depends on the constraint. As you see, this different constraint will result a different punya ni lah. For example, here you state that the constraint kat bawah ni kamu nak letak something yang very flat. So you masukkan constraint tu. So you have this result lah. And this is optional lah, hands on. This is optional because I show to you is very fast one, right? As I explained, I also conducted a hands-on workshop using this ANSYS software. Those interested can fill in this form. The cost will be this will be RM80. Okay, saya letak dekat chat box ni lah juga. Okay, you can fill in this form. The cost will be RM80 lah for 2 days. Okay, if you are interested, you can fill in that form. Okay, then I will contact you and give the details of that workshop. Okay, in that workshop we do the hands-on because now you just see punya tengok je kan. So in the hands-on workshop we'll do step by step and then we'll do it together. You will install that software. If you are managed to install it and you're interested, you can proceed. Okay. If you are not managed to install, you said, okay, tak boleh nak install lah. Tak apalah, jangan register. Sebab you cannot install, then how you are going to do this hands-on workshop, right? So last time I do a 1 day hands-on. Okay. Tak cukup lah kan. Tapi 1 day pun kita mungkin tak buat full lah, kita buat 2 days. Kenapa RM80? Last time saya order bucket kan, 1 jam habis. kat family saya kan, saya belanja pakai. Saya ingat RM80 ni, oh, okay, 1 jam habis. But this one I want to share with you. That's why I said, okay, RM80 2 days lah. Because I want to share the knowledge. Last time I attend one course, I have attend a training in Germany. I've paid €3,000 for 1 week. Okay, I've paid €3,000 for the ANSYS punya training last time lah, right? Last time. But because I want to share with you, right? Those who are interested, okay, can join this workshop. Okay, I think that's all from my parts. That the sharing of the optimization. Okay, for that workshop, will not be focusing on the 3D printing, but is focusing on the optimization. Okay, the optimization can be for the CFD and also the structural, right? Okay, that's all from my parts.